for the invitation and the opportunity to talk to you about blazar science with the knot. Blazars were not a very popular subject of the meeting, so I thought I'll give you a brief introduction so everybody has a rough idea of what we're talking about, and then I'll try to highlight a few interesting topics and areas where knot has been very, very important to us. Of course, there is no way I can cover all the wonderful things that knot has done for blazars over decades now. So I thought I'll just focus on very recent results and just so you have some outlook for the future as well. So blazars are active galactic nuclei with jets. So you have a supermassive black hole in the center of a galaxy. There's a lot of gas, and the gas finds its way to the event horizon by forming an accretion disk. And in a few cases, about 10 to 15%, we see collimated, often highly relativistic outflows flowing from the supermassive black hole. We have many different types of AGN, but what we understand is that we're looking at the same object. It's just the orientation of that system to the observer gives it slightly different properties, and then we would classify that as a different object. That orientation is particularly important for blazars, where the jet is pointed directly towards a line of sight. And this gives them very unique and very peculiar properties. For example, we see superluminal motion. We see jets going faster than the speed of light, and not just 1 or 2 times faster, but like 30 and 40 times faster than the speed of light. Of course, this is not real. We're not violating any special relativity, but is due to the alignment of that jet towards the observers here on Earth. That alignment also makes them basically the top of the food chain. They are the brightest and more variable sources that we see across the electromagnetic spectrum. And you see here an example of what M87, which also gave us the image of the black hole, looks like from radio from the left all the way to TV gamma rays on the right. Of course, the way it appears in different wavebands is related to the capabilities of the instrument. Also, M87 is not a bona fide blazar. It's something we call misaligned AGN. So that's why you get a lot of this beautiful structure. Typically, blazars, no matter the instrument, appear as point sources. So they make very unattractive images, typically. But the same principles that apply to M87 should apply to blazars as well. So this is what we think is going on. You have a supermassive black hole which has an accretion disk. A jet is launched. The jet in the beginning is not very fast, but it accelerates as it moves away from the black hole. It goes through areas where you have a lot of gas, which we call the broadline region. And this is where we think spectral lines are coming from. And then it will continue to accelerate until it reaches terminal velocity in a region we call the core of the jet. The origin of the core is not clear, but people think is most likely a recollimation shock of the flow. And this is where we have a lot of particle acceleration and high energy emission. And after that, we're now at parsec and kiloparsec scales, where most of our emission is dominated by radio. So this is what the spectral energy distribution of blazars looks like. There are, of course, differences between sources, but they all have this very characteristic 2-hump shape. The first one, which goes from radio the way to X-rays, is through synchrotron radiation from relativistic electrons that have been accelerated in the magnetic field of the jet. There are a few reasons why we believe this. One of them is polarization, and we've seen blazars be as highly polarized as 45%, which is very high and not easy to do with anything else other than synchrotron. What we don't understand is how our particles accelerated to the point that can make synchrotron X-rays. And we have 2 competing models. One is that we're looking at shock emission. So this could be either traveling shocks or standing or collimation shocks that will accelerate particles. And the other is magnetic reconnection. So you have layers of opposite polarity magnetic field lines that will come together, break apart, and reconnect, and then you can accelerate particles along those reconnection lines. The high energy component runs from X-rays all the way to TeV, and this is something we don't understand the origin of. But again, we have two competing models for that. One is what we call leptonic processes, and the most relevant one here is inverse Compton scattering. So you have electrons propagating down the jet. They see some target photon field. This could be from the jet itself or some external source. It doesn't really matter, but they will upscatter it to higher energies. The other process, or maybe family of processes, is what's called hadronic. Basically, you have protons that do all the heavy lifting, and protons will make synchrotron, but will also interact with other photons and protons, produce pions, and then pions will decay to secondary particles and also gamma rays. We typically classify blazars in two ways. One is with the location of the synchrotron peak. So if the first hump peaks in the infrared, that will be a low peak source. If it's in the optical, intermediate, and X-rays will be high peak source. And the other more traditional way would be through spectral lines. So if we have very weak or no spectral lines at all, which you see at the top panel, that would be called a BLAC type object. If you have broad emission lines in the middle, that would be a flat spectrum radio quasar. And I just have there what the spectrum of an elliptical galaxy would look like if you remove the blazar from it altogether. So we have a lot of different questions, open questions for blazars, from very basic things like how are the jets formed and what are they made of, to more complicated questions like whether blazars emit high energy neutrinos and ultra high energy cosmic rays. And NOD has been very, very important in trying to address all these questions. And it's really kind of in the sweet spot for what we need for blazars. It's big enough so we can have good quality data across the board, but it's not big enough so that we can still use it regularly. And also when sources go into outbursts, we can still follow them without any problems. So I'll just try to highlight a few interesting topics just to tell you that in blazar science, typically a single wavelength doesn't really tell you much. You need to know, you need to see the multi-wavelength picture, and you need to understand what you see in one waveband translates to what you see in others. So a lot of the science with NOD has been driven by the MAGIC people. The MAGIC is the Cherenkov telescope, which is located in La Palma. It's actually very near the telescope, and I was told that we get to see that tomorrow. And what people have been trying to do over the years is to organize the broadband multi-wavelength campaigns, looking at sources both in different states, and try to build this simultaneous or quasi-simultaneous spectral energy distributions where you can fit models to it and try to understand what's the underlying processes and what's triggering different states. So what I have here is a recent paper from MAGIC where they looked at one of the very few sources we know that is being gravitationally lensed. And as you can see here, it's very important to have broadband infrared and optical coverage, which helps you really to constrain the shape of the first hump, and then that basically regulates what's happening at the high energy. So through a lot of effort, we're coming to a consensus that the SED of blazars is most likely dominated by leptonic processes. So we're learning something about the composition of the jet and maybe how the jets are formed. Another very important aspect of photometry that NOT has been very good to provide has to do with host galaxies. And host galaxies, as you know, are very important in our understanding of the environment of the sources. But in the case of blazars, might also help us understand jet formation and jet triggering in some sense. Now, for the big scary blazars, we don't get to see the host galaxy. The jet typically outshines everything by a few orders of magnitude. But there are weak blazars. Those are almost 100% BLAC type objects where we can study the host galaxy. And these sources are particularly important because they might be faint in optical, but they're very bright in gamma rays, and they're also bright in TeV gamma rays, which is one of the reasons I'll come back in a minute. So with studying the host galaxy, we can also get estimates for the redshift, which is very important because if you remember, the BLACs don't have any or very weak spectral lines. Of course, the king of redshift estimation is spectroscopy, and NOT has also been very, very helpful with that. And you can see here an example of a gamma ray source. Well, this is a spectrum taken from NOT. And as you can see, you really need kind of good data to get something out. And what you also need in case of blazars is you need to have fast response capabilities for your spectroscopy. And you saw this morning an example of how the jet emission in blazars can completely swap the emission lines. So people are doing kind of the opposite game. They monitor sources and they try to see when the jet becomes dim so they can, trigger spectroscopy and maybe try to get something out of it. Redshift for gamma ray sources is very important for one particular reason, and that is that we have a gamma ray horizon. There is a limit to where gamma rays can reach us from the distant universe, depending on their energy. And this is what you see here. This is the highest energy gamma ray detected versus redshift. You see how it kind of quickly goes down in energy. This is because the high energy gamma rays will see the extragalactic background light and they will be absorbed. So having a lot of sources with redshift estimates at high redshift that are gamma ray bright will help us constrain the properties of that EBL, and then in turn we can learn something about the star formation history of the universe, but also constrain cosmological parameters. And you've heard a couple of days ago, and I think there's another talk today, about the Hubble tension and the differences that we see between the late and the early universe, and this can be very helpful. This is also particularly important for the upcoming Cherenkov telescope array era. This CTA will be the next generation high energy gamma ray telescope. It will be many times more sensitive than anything we have available today. And it will have two sites. One will be in the south, one will be in the north, and the north side will actually be in La Palma. So it will be very near the MAGIC telescopes, although the exact location and configuration is still under discussion. But you can imagine there will be plenty of opportunities for synergies and a lot of interesting science between CTA and NOT, of course. And finally, I want to talk about polarimetry. And this, I'm a bit biased because this is my favorite thing. So there are two ways we can study blazars with polarimetry. One is long-term monitoring. So we try to build light curves and then try to identify interesting phenomena in those light curves and see how those, again, translate to other wavelengths. And you can see here in this example how variable polarization can be for blazars. This is a paper that we're about to submit where we looked at a source called PG1553. This is one of our best candidates so far for quasi-periodic oscillations in gamma rays. And as you probably know, NOT has a long history of supermassive black hole binaries and other periodic phenomena, started with, of course, OJ 287, which is our best supermassive black hole binary candidate at the moment. So in this paper, we try to understand the multi-wavelength variability of the source and whether that QPO behavior we see in gamma rays translates to other wavelengths. Just as a spoiler alert, it doesn't. And of course, we try to look at what polarization is doing, and Talviki Hovata and Kari Nilsson, which some of you might be familiar with, made this model where you take a precessing jet and you predict what will be the polarization modulation of that. And this is what you see in the orange lines there. So they can actually reproduce the total intensity. They seem to be able to do a good job with the polarization angle, which is the middle panel. but all the different models and the different kind of configurations give very low levels of polarization degree. So maybe a precessing jet is not the right model for this source, but this is under investigation still. And the other way not can be very important, has to do with time domain and the capabilities of coordinating with other instruments and following blazars. And I think one of the very interesting synergies at the moment is with the high energy polarization and the Imaging X-ray Polarimeter Explorer, or IXP. This is the first mission that is capable of measuring X-ray polarization from many different sources other than the Crab. And it was launched just December of this year. So we're actually running our first about 6-7 months of operation now, and we're already learning a lot about the universe, and of course we're learning a lot about blazars. So what you're looking at here, that is the first detection of X-ray polarization from a supermassive black hole, a source called Markarian 501. And as I've told you, blazars make very lousy images. But what we might be slightly more interested in is this part here. This IXP has 3 identical detectors, which are slightly rotated with respect to each other, and that allows us to take out instrumental polarization. So what you see here, that's the Q and U space, where the colored plots, the colored points are the 3 different detectors. The black is the sum version, and then the purple, or should be purple, color there, that's what we call the MDP99. That's the minimum detectable polarization at the 99% confidence, which comes from the instrument alone. So we have a fairly solid detection of 10% in that jet, which means absolutely nothing. You need to put that into context, and this is where not really comes in. And I'm showing you here what the X-ray polarization versus the optical is looking like. And the different lines you see there are the popular and very kind of frequently used models in the literature. And because we had not in polarization, we were able to actually demonstrate that they're all wrong. And in fact, the model that's more probable is kind of the outsider, where you have an electron population that's been accelerated and then advected down the jet. So different wavelengths come from different regions and see a different magnetic field, and the result is a very chromatic behavior in the polarization degree. For this case, there were other telescopes that help us confirm our results, but there have been blazars where we only know data were available, and they actually agree with this result. But if it wasn't for, as I mentioned, the time domain capabilities in polarization that NOD has so generously provided, then the IXP data would have been basically useless. So we're very thankful for that. So just for people that might be interested, we have about 7 different working groups. We're basically looking at everything that's bright in X-rays and hopefully polarized. And we have observed already a bunch of sources that some of you might be familiar with. We have our first paper out, which is about a magnetar, but there are many more on the way. So just to summarize, NOD has really been instrumental in studying blazars all those years, and we really hope it will continue to do so. It really gives us everything we need. NTE will give us most of what we need, so that's exciting. And I was very happy to hear 2 days ago that polarization is not lost to us, or at least there is a chance that we might get an imaging polarimeter, which I think it will benefit not only blazars but a lot of other science, as we've seen in works. Thank you very much.